ओके सो आज हम अक्टूबर नवंबर 2018 का ही पेपर करेंगे फिजिक्स का, ठीक है। सो लेट्स गेट स्टार्टेड। सो पहला पोर्शन एमसीक्यूज का ही है। Which of the following quantities could have the units of Newton meter per second? Newton meter per second means Newton multiplied by meter divided by second, which means force multiplied by distance divided by time. Force into
Oh, okay.
distance is work, work divided by time, which is power.
Power. But wait, how is it divided by time?
The power of second is -1.
But it is also okay. Right.
It's negative. Negative means it's dividing it. Now,
Okay.
the equation W equals Fs can be used to calculate the work done on an object by a force. Each quantity in an equation can be described as either a vector or a scalar. Select the row from the table that correctly describes each of the quantities in this equation. All you need to do is just identify which is a scalar and which is a vector. So force is a vector, right? That's what you know from your, okay, all of them are vectors. Work is a scalar quantity, so it's either A or B. Displacement, this is displacement, okay, not distance. Displacement is vector.
Vector.
It's B. A spring is suspended from a bar. A load of 2.5 Newton is added to the free end of the spring and the spring extends by 4 centimeters. The load is increased to 10 Newton and the spring extends by a further distance of X. What is the value of X? Okay, so they just want us to calculate the value of X, which if you compare with the original spring, in the third diagram, the total extension is not just X, but rather it's 4 plus X. If you compare it with the original spring, in the third diagram, the total extension is going to be 4 plus X. So now if you use the second diagram to calculate the spring constant, use Hooke's law, F is equals to Kx. K will be force divided by the extension. 2.5 divided by 4 will give you 0.625. 625. Okay, this is in centimeters. Okay, we are gonna keep it in centimeters because we need the answer in centimeters. Now use the same in the equation. 0.625 x. Okay, actually not x, I should rather say extension. So instead of x, I'm gonna write e. Okay, now we know the force is 10 Newton. We know the spring constant is 0.625. We know that the total extension in the third diagram is 4 plus x. Okay, it's not just x, it's 4 plus x. Add that in and solve it, you'll get your answer. So this is going to be 10 upon this answer and then 4 minus x, so 4 plus x actually, so it will go there. The 10 upon 0.625 minus 4 give you x, and calculate that please. This is going to be 10 upon 0.625 minus 4, which is 12 centimeters. It should be option number C. Get it?
Yeah.
Okay. Yep, it's option number C. Then going on to question number 4. A student takes measurements to determine the density of a metal in the form of a long, thin wire. Which of the following gives the equipment he should use? Okay, we have a wire. We need to calculate its density. The formula for density is mass upon volume. Mass divided by volume. For a wire, the mass can be calculated by a top band balance. So that's given in all the 4 options. Now for the volume, well, for the volume, we need this cross-sectional area and the length of the wire, because cross-sectional area, when gets multiplied by the length, will give us the volume, right? Now, what's the formula for cross-sectional area? It's gonna be pi r squared multiplied by the length, right? The the area of the circle, and when you multiply it with the length, you'll get the volume. So this is also a radius, and this is a radius. Okay, to calculate the radius or diameter, we either use a vernier caliper or a micrometer screw gauge, right? But since in the question they told us that it's a thin wire, for a thin wire we use micrometer screw gauge. Okay, so this option A is the best choice.
Okay.
Okay, moving on. A box is pulled up a ramp using a rope as shown. The box moves at constant speed. The speed is constant. Okay, that's the key term. Speed, constant speed implies that the kinetic energy is also constant. So it means there is no work is done on it to increase its kinetic energy. Okay. Now the forces acting on the object are the following. Okay, there is a weight of this object. There's a frictional force acting on the backward direction. If the unit is capital F. There's a tension in this wire, and there is a normal reaction force perpendicular to the plane. Then they are saying select the diagram which represents the free body diagram. Okay, so we just need to match these forces with the diagram. So weight is downwards, forces backwards, tension is there. So option A is the best one. Whereas if you look at this one, what's the problem in this one? Weight, force, R, T, okay? It's exactly identical. Why have they given us the same option 2 times? Normal reaction.
What is the question?
They're asking us
Yeah.
the forces acting on the box. Select the diagram which represents the free body force diagram for this object, for this box
Okay.
actually. If you look at this, these two diagrams are exactly identical. See, the real
Ah.
time, force. Maybe this is
No,
a
no, no, no. It's not. It's not. It's not. The top part is like the R and the no. I think the R and W and C part is almost equal, and in A,
oh yes,
the
yes,
R
it's the length.
and
It's the length. Smart, smart.
yeah.
Now you're getting it. So it's not A. It's not A. The length of the arrow represents the magnitude, okay, and since it was moving at constant speed, that means there is the net force acting on it is 0, right? If the constant speed means net force is 0, means acceleration is also 0. So for in that case, the tension and the force have to be equal. So it's not A, it's rather it's C. It's the length of the arrow. The forward and the backward forces must be equal. Yep. So that's C. Clear?
Wait. No, can you explain again?
I'm saying they told us it's moving at a constant speed, meaning acceleration
Yeah.
is 0.
Is it?
If acceleration is 0, net force is 0. If net
Yeah.
force is 0, then that actually means the tension has balanced the frictional force.
Okay. Right.
So they are in the same magnitude. So their lengths must be equal. In the first one,
Okay.
the length of the tension is longer than the force. Clear?
Right.
And moving on. A student drops small solid spheres through a liquid of viscosity. Okay, this is called eta. Okay, ETA, eta. Viscosity eta in a measuring cylinder. A small sphere of volume V falls at a terminal velocity through the liquid. A large sphere of volume 8V is made of different material. The largest sphere falls through the liquid at the same terminal velocity. The frictional force acting on the small sphere is F. What is the following? Which of the following is the frictional force acting on the larger sphere if it is moving at a terminal velocity and has a larger volume? Okay, so what was the viscous drag force formula? It's eta
S-
6 pi RV,
R.
R multiplied by terminal velocity. Okay, it's actually 6 pi eta RV. This is the formula according to Stokes' law that we learned. Now they're saying that these two are traveling at the same terminal velocity. This means the force that is being applied on this larger sphere is the same as the force which is being applied on the smaller sphere. That is, the upward force and the downward force on both the spheres is balanced, due to which they move at the same terminal velocity. The terminal velocity at which they fall is exactly the same. So the radii, although the radii are different, but eta is the same. The terminal velocity is also the same. And that implies the force, in order to keep this terminal velocity constant, there has to be something different with the force, right? Okay, let me rearrange this formula. If you rearrange this formula, it becomes V is equals to F upon 6 pi eta multiplied by r. Now this r is constant. Sorry, the v is constant, the terminal velocity with which the two are moving, but the r is different. If the r is different, then that actually means this f also has to change to keep this v constant. So can I say that this force, the frictional force acting on the larger sphere is actually proportional to the radius of that sphere? Can I say that from this equation if the terminal velocity is constant? Let me re-explain that point. Basically, if you look at this Stokes law again, F is equal to 6 pi multiplied by eta multiplied by radius multiplied by velocity. Now, instead of writing this as radius into velocity, I'll write it as velocity into radius. This entire factor is constant because the terminal velocity is the same, the eta is the same, and 6 pi is constant. This is constant from Stokes' law. So can I say that the force, the frictional force that is acting on the larger sphere or the smaller sphere is actually proportional to their radii? I can say that. So if I can say that, then that means I'll need to see what's the difference in the radii after the change in volume. The formula for calculating the volume of a sphere is 4 upon 3 pi r cube. Now, the volume of the smaller sphere is V when the radius is, let's assume it's R. Okay. Now, if the volume changes to 8V, what will the new R become? You don't need to cross multiply this time, okay? You just need to put it into this formula.
Sir, you're lagging.
Right, so I was saying that F is equal to 6 pi eta multiplied by V multiplied by R. This is your Stokes law. If 6 pi eta and V are constant, velocity is constant, the terminal velocity is constant, then force and radius are proportional to one another. So we need to see what's the change in the radius for this bigger sphere. To find out the change in the radius, we'll need to use this formula for volume. But even if you look at this formula, the volume itself is proportional to the cube of the radius, right? If it is proportional to the cube of the radius, then we don't need the entire formula. We could just use the ratio method over here. For the ratio method, it's going to be volume 1 upon the second volume is equal to radius 1 cube divided by radius 2 cube. This is how you're going to use the ratio method when the powers are not 1. Okay. Now, once you've done this, you have the new volume, you need the new radius. Your initial ball had a volume of V, and let's assume its radius was R. Now the new ball has a volume of 8V. We need to find out its radius. We need to find out R2. Let's plug in the values over here. Instead of V, I'm going to plug in, instead of V1, I'm going to plug in V for the first ball. And for V2, I'm going to plug in 8V. For the first ball, I'm going to plug in R cube. For the second ball, I'm going to plug in R2 cube. And we need the value of R2 cube. Okay, so the V and V will cancel each other out. Okay, now if I cross multiply them, I will get R2 cube, which is equal to 8 times R cube. Now to remove the cubes, I'm going to take the cube root on both the sides. This is going to become R2 is equal to the cube root of 8 is 2, and 2 multiplied by R actually. Okay, so the second ball has a radius which is double the original radius. And if it is double the original radius, that means the force which it experiences will also be double because they are proportional to one another. Option should be C. Get it? If a liquid is cooled, the terminal velocity of the sphere would change. The terminal velocity of the sphere will it increase, decrease? If the liquid is cooled, the viscosity of the object, the liquid will increase. The viscosity will increase. F is equal to, meaning the viscous force will increase. So F is equal to 6 pi eta multiplied by R multiplied by V. Now the viscous drag will increase, and if the viscous drag...
What do you mean by terminal velocity? Like it would increase or decrease? Like terminal velocity stays the same, right?
Yes, but will it reach terminal velocity first quickly or will it reach terminal velocity later? It's gonna stay the same if
attain it.
I'm saying that will it reach terminal velocity quickly or will it reach terminal velocity late? Will it reach to a smaller value of terminal velocity or will it reach to a larger value of terminal velocity? Because terminal velocities also can have different values for different conditions. Meaning, if I say the terminal velocity is 10 meters per second, then that means it won't change. But for another ball, if I say the terminal velocity is 5 meters per second, then it will stay 5 meters per second and will not change. This is what I mean by change. Terminal velocity. Yeah, meaning a different velocity with which it will fall then. Now they're increasing the viscosity. By the way, this eta itself is also a viscous force. Sorry, actually the viscosity is this eta. And what's the relationship of eta with the terminal velocity? For that, we'll need to rearrange the formula. If you rearrange the formula, it becomes F upon eta is equal to 6 pi r v. Now 6 pi r is constant and f is constant. Let's assume f is constant, f is not changing. And now you are increasing the eta. Will that decrease the viscosity? Sorry, will that decrease the terminal velocity? That would decrease it because they are inversely related. So it would decrease because n would increase. B should be the correct answer. That's the answer. Basically, you could think of it this way. A ball is falling with its weight, and now if you increase the viscosity, then the upthrust force will increase at a faster rate and will balance out the weight. Okay? The upthrust force will balance out the weight more quickly, and if it balances out, the faster it balances out the weight, the smaller the value of terminal velocity the ball reaches.
Okay.
Yeah. So if you increase the value of this by increasing the viscosity, then the terminal velocity would decrease. So B. Ball is dropped and is caught after the first bounce. The ball takes 1.6 seconds to reach the ground. From what height would the ball be dropped? It's dropped, and the height is needs to be calculated. Acceleration is 9.81. Time taken is 1.6. It's dropped means initial velocity is 0. Which equation of motion can we use?
Is equals to ut plus half at square.
Yes, and u is 0. So this entire factor becomes 0, and it's going to be half times
So half
9.8
into 9.8
into 1.6 squared. And you can calculate that and get your answer, okay? I'm not doing this. Moving on. Which of the following is the velocity time graph for the motion of a ball? Okay, this ball which is dropped from a certain height and then is caught after the first bounce. So it drops, it hits the ground, and after it bounces first, it is caught. This means when it is caught, it has some height above the ground. Which of them is the velocity time graph? They want us to draw out the velocity time graph. That if you look at this this situation over here, the velocity is positive in one case and negative in the other, or the other way around. It can be negative over here and positive over here, as long as the two signs must be opposite to one another. So let's assume, and yeah, one more thing, just before hitting the ground, the maximum velocity that this ball will reach is gonna be greater than the velocity with which the ball leaves, okay? Meaning it would come, it would, just before hitting the ground, its velocity would be, let's say it's somewhere around 20 meters per second. Then as this ball leaves the ground, its velocity would be less than 20, okay? Because usually when the balls are dropped and caught after the first count, energy is lost, and it's usually an inelastic collision. And even if you look at the graph, these two velocities have different values. The negative and the positive velocities have different values, okay? So now let's look at the graph which is showing us the motion of this ball. Initially the ball had 0 velocity. This graph should start out from 0 because it's dropped. Neither A nor B can be the answer. Then the ball reaches a maximum value which is going to be either equal to the velocity with which it leaves or greater than the velocity with which it leaves. Let's assume it's greater than the velocity with which it leaves. This 20 meters per second is greater than the velocity with which the ball rebounds. So if it is greater, this velocity that it will reach to, it will be higher than the other peak. As soon as it reaches its maximum value, it hits the ground. Okay, as soon as it reaches its maximum value, it hits the ground. And as soon as it hits the ground, it suffers deceleration and reaches a negative value. This negative value is less than that positive value because some energy has been lost. It's inelastic collision. And then the ball reaches the value of 0 again. The velocity of the ball reaches 0 again when it reaches its maximum height over here. So it's going to be option number D. It cannot be C because in C, if you look at the velocities, the positive velocity is less than the negative velocity, which is wrong. The positive velocity can either, this, by the positive, they mean this part of the journey. So this velocity can either be equal to or more than the velocity with which the ball leaves. Okay, it can never be less than the velocity with which the ball leaves. It cannot be C. D is the answer. Get it? Okay. Number 10. Two liquids of different viscosities flow through identical pipes. If the conditions are identical, the liquid with the lower viscosity will, lower viscosity means lower fluid friction. So what will happen to it? It will flow at a lower speed and transfer a constant volume of liquid per second. It will flow at a higher speed and transfer a greater volume of liquid per second. It will flow at a lower speed and transfer a greater, or it will flow at a higher speed and transfer a smaller volume of liquid per second. So first of all, its viscosity is less than that, means it will flow at a faster speed, not at a slower speed. Then if it is flowing at a faster speed, then of course per second also refers to the speed, right? The flow of volume per second also indirectly means speed. So if the speed is higher, then obviously the volume of liquid per second transferred will also
Yeah.
be higher. So B is the
Okay.
answer. Okay, MCQ is done. Theory. State what is meant by the gravitational field strength. They are asking us the value of G, which you know it's 9.81 Newton per kg. The force per unit mass at a point. Force per unit mass at a point. I gave you this definition
Yeah.
in theory. Then after, okay, after this, part 2 says they're asking for the center of gravity. This is a
The point
point,
at which the mass of the object acts upon.
point where all the mass appears to be concentrated, or a point through which all the weight of an object is assumed to act. It is a point where the gravity appears to act. Okay,
Okay.
center of gravity. So a point from where the weight of the object appears to act.
Oh, and what if we write mass instead of weight?
No, that's gonna be wrong because center of
That
gravity itself is another definition. Sorry, center of mass. Center of mass
right.
is another thing.
Okay.
So a point from where the weight of the object appears to act. The gravitational field strength on Earth is 9.81 Newton per kg. Show that this results in an acceleration of free fall of 9.81 meters per second squared. They've given us the value for gravitational field strength, which is 9.81 Newton per kg, and they want us to show that the acceleration of free fall of an object on Earth is this much. Okay, during free fall motion, it's always assumed that the air resistance is 0. This is a fact to remember. But air resistance is 0 during free fall motion. during free fall. Then that means if an object is falling, it will purely be acted upon by the weight of that object and not by the other resistive forces during free fall motion. From Newton's second law, we know that force is equal to mass multiplied by acceleration. When the object is falling, we assume that that object has a mass of 1 kg. Okay, assuming that the mass of the object is 1 kg. So the value of mass is going to be 1 kg. We need the value of acceleration, and the force or the weight that acts upon that object, the weight that acts upon that object is the 9.81. Its value is 9.81, because if you remember that from W is equal to mg, the weight of an object is mass multiplied by the gravitational field strength, and the gravitational field strength is 9.81 itself. So the weight is 9.81 Newton for 1 kg mass. To multiply them, the acceleration also turns out to be 9.81 meters per second squared. That's why acceleration of free fall motion is 9.81 meters per second squared on the surface of Earth. Clear?
Yep.
And this can also be called the resultant force attacks. Okay, resultant force is the weight of the object, which is 9.81 Newton. Question number 12. Two students carry out experiments to measure the acceleration of free fall, calculating the value of g now. In each experiment, a ball bearing is dropped through a known distance, and the time taken is measured. Okay, so some distance is determined, and a ball is dropped from that distance. And as soon as the ball reaches the end of that distance, the stopwatch is stopped, and the time is recorded. Student A drops a ball bearing and starts a stopwatch. Stops the stopwatch when he sees the ball bearing reach the ground. Okay, when he looks at the ball bearing as it touches the ground, stopwatch is stopped. And it measures to the nearest 0.01 seconds. What is this value? This is called the precision of the stopwatch. Okay, by the precision we mean the smallest value that the stopwatch can measure is precision of that stopwatch. If it would have been, precision is better when this value is small as possible. Okay, by a better precision we mean a smaller precision. Student B uses an electronic system, a more advanced technique, that releases the ball bearing and simultaneously starts a timer. So as soon as that electronic system releases this ball bearing, the timer is started, and as soon as this ball bearing stops, the timer stops automatically when the ball bearing reaches the sensor. The sensor is attached over here, and as soon as the ball bearing hits the sensor, the stopwatch is stopped. So a more accurate method, because as soon as the ball bearing will hit it, it will automatically stop. And the precision is smaller. It's 1/10 of that time. It's 0.001. Over here, it's just 0.01. Okay, so this is a better precision. Now the question says, state and explain two reasons why the student method used by B is better than for the experiment. Okay, so we need to suggest and we need to explain two reasons why this student B's method is better than student A's method. Okay, first of all, when the student A will be dropping the ball, it's very unlikely that he would drop the ball from rest, because as soon as a person drops a ball, inevitably he might apply some force on it, and the initial velocity of the ball might not be zero, right? So student B and student A might not drop the ball from zero. Drop ball from rest. That's the reason, and the explanation for this reason is because inevitably some force would be applied, and inevitably some force would be applied by the some force will be applied by the student. This is the first reason. The second reason that we could explain, if you look at it, the ball bearing, as soon as it is dropped, the timer is started, and then as soon as it touches the base, the timer is stopped. If you are counting the time or measuring the time manually, then there is a very big chance of reaction time error or human reaction error. Human reaction time error, right? We might not stop the watch at the same time as it is stopped, as the ball hits the ground. So reaction time over here, this as this person itself, if he does that, then the reaction time is gonna be larger as compared to the machine itself. So a larger reaction time for the person, larger reaction time for student compared to the machine. Okay, and well, one of the reason why this reaction time might be larger is because of the precision as well. If you look at the precision is much smaller for the machine as compared to the student. So since this precision is larger, then that means the reaction time would be greater for the student. Okay, larger reaction time for the student compared to the machine, because the precision or the least count is larger for the student B. For student A, sorry, not B, for student A. So the larger the least count, the greater would be the reaction time. Apart from that, well, two are needed, so yeah, we've done the two. 13 says a crane is used to remove an object from the bottom of a lake. Object is a cylinder of height h, and the depth of the lake is d, as shown in figure 1. Where is it? It's right over here. This is the lake, depth is d, and the height of the object is h. The cylinder is moved vertically to the water at a slow and steady speed. Then the cylinder comes to rest in a position where it is completely above the surface, as shown in figure 2 over here. The graph shows how the tension in the cable varies with the distance as the cylinder is lifted from the bottom of the lake to the position in figure 2. The key term over here is steady. Steady means again constant speed. What do we mean by constant speed? Constant means net force is 0. So no acceleration. Acceleration is also 0. Right, that's the key term to identify. Now let's see what's happening. This is the graph which is shown of the tension. The tension initially is constant and is at a lower value. Then the value of the tension increases at a constant rate, and then it becomes constant again at a bigger value. Now, this is P and this is Q, and this is the distance moved by the cylinder. State the expression for the distances P and Q. Distance P. What is P? Okay. And this is Q. Distance moved expression. The P would be the distance of this cylinder as it is moving up through the lake, and then Q might be the distance as it goes above the ground. So Q, distance Q and distance P. Let's see. Oh wait, basically over here, if you look at it, the tension has reached a maximum value, and over here the tension had a lower value. When the this cylinder was inside the lake, this was the tension that was acting upwards. In addition to tension, what are the forces acting inside the lake? There's an upthrust force, which is also acting inside the lake due to difference in pressures, right? The tension inside the lake would be at a lower value, a smaller value. But as soon as the distance is moved, as soon as this block is moved upwards and it moves up, and as soon as it reaches this surface, that's the point where this block itself has the tension in the cable at this constant value. Okay, this is the point where the tension is present. And as long as this object is submerged inside the water, the tension will stay constant. Reason for that is because upthrust will stay constant. If you look at the value of upthrust can be calculated using the formula rho v g. G is constant, the rho is constant. Rho is the density, G is the gravitational field strength, but V is the volume of this object. And as long as the volume of this object is submerged inside this lake, upthrust will stay constant and the tension will have a constant value. So as long as this object, so what is P? P is this distance till here. Basically, this is the distance that this block has covered so far. This is the distance P.
P?
Yes, P.
But isn't
Till here, till the base. And then as soon as this base moves out, as soon as the base moves out, what happens to the tension? As soon as the base moves out, the upthrust automatically becomes 0. Because now, as this object is outside the water, there will be no upthrust force because now the rho has become 0. And so that's why at this particular point, when this object immediately after it moves out of this lake, the tension would reach its maximum point. And therefore, this entire distance that this object has covered is going to be the distance Q. I'll repeat this. Basically, just look at the base of the object and measure the distance that the base covers. This is the base. This is the base. And initially what happens, this object moves up, 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 and reaches this point. And let's assume this is the object till this point. Okay, this is the height of the object. If you look at the base of this object, the base has covered how much distance? This is the distance that the base has covered as long as this object was submerged inside water. I'm taking the value till this submerged part because this is the point till which the upthrust will have a constant value. As soon as this object moves out, upthrust will fall to 0. And as soon as the upthrust falls, this graph will rise. Okay? So this is the point. This is the distance P. This is the distance till which the tension has a minimum value. As soon as this block moves out, the tension will reduce back to 0. And as soon as this object moves out, this Q, if you look at the Q, it's directly immediately after this steep line and immediately at the start of the horizontal line. Immediately after the steep line means immediately after this block moves out. Immediately after this base reaches this point over here on top, that's the point Q. That's the distance Q. So what is Q? Q is actually this entire distance. And what is P itself? P is actually this entire distance D minus the height of the object. Entire distance D minus the height, and Q is the entire distance D. See, what is the value of P? It's this entire distance minus the height of the object. What is Q? Q is this distance, T. Get it? Okay, so before P, before the point P, tension is constant, right over here. Weight is equal to the sum of the tension and the upthrust. Upthrust depends upon the volume of the object itself. So it's constant because the volume is constant. Tension has a constant value too because the upthrust is constant. Then as the object is pulled out of water, the upthrust decreases. As it is pulled out of water, upthrust will fall, right? So if the upthrust falls and we need to keep the speed constant and keep the net force zero, then the weight has to be balanced by the tension. So if the upthrust is falling, the tension has to rise. So as the upthrust, as soon as it completely leaves the water, over here, upthrust decreases, so tension increases to balance the weight. As soon as it completely leaves the water, tension becomes constant, which is, and this constant value is greater than the initial constant value of the tension. It is above the initial value because now the upthrust has become zero. Tension balances the weight since the object moves at constant speed, and the net force is zero. Or I don't know how to pronounce this term, but I'll call it Soyuz. Spacecrafts are used to carry crew and supplies to the International Space Station. The spacecraft consists of rockets, fuel tanks, and capsules to carry crew and supplies. Okay, this is your spacecraft with the capsule and the rockets. During takeoff, combustion produces hot gases at high pressure. The gases expand and move downwards out of the rocket. Explain how this enables the spacecraft to accelerate away from the ground. Okay, so the spacecraft, while it is accelerating, it emits gases, high pressure gases downwards. If high pressure gases are emitted downwards, the gases, high pressure means there is some force applied on the gases by this engine. If force is applied by the engine on the gases, this means the gases will also apply an equal and opposite force on this spacecraft, right? According to Newton's third law. And so if they'll apply equal and opposite force on the spacecraft, they'll allow it to then allow this spacecraft to accelerate upwards away from the ground because the gases are ejected in the direction of the ground. Okay, so they exert an upward force, and so there is now a resultant upward on this force, which results in the acceleration of the spacecraft. Okay, 2 marks. If it was for 3 marks, you could have given reference to Newton's third law as well. Okay, so gases exert upward force on the spacecraft, resulting in a net force in the upward direction. And as you know, if the net force is in the upward direction, then of course the acceleration is also going to be in the upward direction. Therefore, acceleration is in upward direction. Moving on. As the spacecraft takes off, apparent weight of the crew member is 3,700 Newton. Determine the acceleration of the spacecraft when the mass of the crew member is 81 kg. Remember apparent weight while the object moves upwards. When the object moves upwards, the apparent weight increases, right? Apparent weight is equal to the acceleration plus the actual weight. Actual weight plus MA. mg plus MA. What's the actual weight? It's going to be 81 times 9.81 plus the acceleration of this crew member. Okay, acceleration needs to be calculated. The mass is 81 times the acceleration of that spacecraft. Apparent weight is 3,700 Newton. Now you rearrange it and get the value of acceleration. 3,700 minus 81 into 9.81. You divide it by 81. You get the value for acceleration. This turns out to be how much? 3,700. Okay, keep the multiplied signs in brackets. Okay, so as to avoid any error. What's your answer? I'm getting 36 meters per second squared. Are you getting the same answer?
Yeah. 35.8. That's 36.
Yep, correct. So apparent weight is when the object is moving up, apparent weight equals the actual weight plus the net force is your apparent weight. Whereas if the object was coming down, then the apparent weight would have been the actual weight minus the net force.
When?
If the object would have been coming down, then the apparent weight equals the actual weight minus the net force. Get it? Or you could just remember it this way. mg plus ma and mg minus ma. Just remember it this way. Okay, this is for going up and this is for coming down. Get it? Part C, as each fuel tank becomes empty, the tank and its associated rocket are detached from the spacecraft and fall back to the Earth. Explain why this is done. Okay, so as the fuel tank is emptied, the fuel tank is of no use then. And the fuel tank itself would have some weight, right? In order to propel the rocket upwards and in order to save fuel, save more fuel, prevent more fuel from burning, prevent more fuel from doing work in carrying the empty tanks, it is thrown back to Earth. Okay, it falls back to Earth. That's the reason. This will actually reduce the weight, reduces the weight of the spacecraft. If it reduces the weight, then what would happen? The weight is pulling it downwards, right? We need upward force. So the net force, if this weight is reduced, then the net force in the upward direction will also increase. Yeah. The net force in upward direction will rise. Part D, when the capsule returns from the International Space Station, parachutes are used to reduce the speed of the capsule as it nears the surface of the Earth. Explain why parachutes reduce the speed of the capsule. Parachutes, what do? Do they increase their air resistance? Definitely, they increase the air resistance. If the air resistance is increased, initially, while the rocket was coming down, it had some weight which was pulling it down. But now, if air resistance increases, then that means there is a net force upwards, right? There's a net force upwards. If the air resistance increases and becomes more than the weight, then there would be a net force upwards. And if there would be a net force upwards, then that would actually lead to deceleration of the spacecraft. Why deceleration? Because now the net force would be in the opposite direction to the velocity of that spacecraft. Okay, velocity is downwards, but the net force is upwards. So parachute provides more air resistance, which results in upward net force, upward resultant force. So that is in the opposite direction to the downward velocity. So the net force causes deceleration. F net causes deceleration and hence reduction in velocity. Reduces velocity. Get it?
Yeah.
There's an additional point written in the marking scheme as well. It says that the air resistance, the cross-sectional area is greater, large cross-sectional
Yeah,
area.
this
So,
was in my mind.
okay, so you should have told me. A cross-sectional area is greater. This point had a mark. Without this point, we would have gotten only 2 marks. So cross-sectional
This was
area,
the first point that came into my mind.
and this is the first point written in the marking scheme. Cross-sectional area of parachute is large. Okay, it increases the cross-sectional area, so therefore it increases the air resistance. It results in an upward net force, and hence results in deceleration and decrease in velocity. Now coming to projectile motion. Two projectiles A and B are launched from position O at the same time. At time t, both projectiles travel the horizontal distance OP as shown over here. Okay, this is one projectile, this is a complete projectile, and that is somewhat half projectile. And they have been thrown with different velocities at different angles. Projectile A is launched at this velocity at an angle theta. B has been launched with this velocity at an angle 45. Show that UA may be expressed in terms of UB as in the following way. Okay, we just need to show that UA equals 0.707 times of UB upon cos of theta. So let's see. Okay, this is 45 and this entire angle is theta. If this entire angle is theta and the object is moving, now see in the first line of the question it says that they have traveled the same time. At the same time, they have traveled the same horizontal distance, OP. Let's assume OP has a value of S. Okay. In the horizontal direction, both of them have constant velocities, right? For if you talk about UA, this is UA at an angle theta to the horizontal component of velocity is going to be UA cos of theta, correct? The horizontal component of UB is going to be UB cos of 45 degrees because that's the angle over here. Once you have the two velocities over here, then you've been given a time period during which the distance they both of them traveled was the same. Distance traveled by A is equal to the distance traveled by the B. This is the first statement that you must write. And you know that distance in the horizontal direction can only be calculated using only one formula because the horizontal direction, this horizontal motion is uniform motion. It's not accelerated motion. Now, for the distance traveled by A, this is going to be VA. For the distance traveled by V, this is going to be VB. The distance traveled by A can be, for the distance traveled by A, you're going to place VA times T. VA times T. The value for VA is UA cos of theta. So UA cos of theta multiplied by the time must equal the velocity of B, UB. Velocity of UB is UB cos of 45 multiplied by its time period. Okay, the two times are the same, so cross them out. Cos of 45, if you calculate it, this turns out to be 1 upon under root 2. This is UB upon under root 2 is equals to UA cos of theta. And now if you rearrange it, it's going to become, oh, okay, this is 1 upon under root 2. 1 upon under root 2 actually has a value of 0.707. So this can be written as UA cos of theta is equal to 0.707 times of UB. And now just make UA the subject and you have your expression. Clear? Shown. Distances they traveled after the same time are the same. Distance by A equals distance by B. Distance traveled in horizontal direction is traveled by the horizontal component of the two velocities. Horizontal component of UB is over here and by UA is over here. So distance is SVT. For SA, the distance by A is going to be UA cos of theta times T, the horizontal component of A, and UB cos of 45 times T, the horizontal component of B. Times will get cancelled out because they are the same. UA cos of theta equals UB upon under root 2. Cos of 45 is under root 2. 1 upon under root 2. Its value is
Wait, how did
0.707.
under 2?
Value of cos of 45 is 1 over under root 2, which is actually the same thing as saying 2 under root 2 upon 2 in your calculator. And it is equal to 0.707. Okay?
Oh, okay.
So this is 0.707 and you plug it in and you show it. Explain why for the paths of the two projectiles should be as shown UA must be greater than UB. Why must UA be greater than UB? Any suggestion? Because the theta is larger, right? The theta of UA is larger. And when you take the cos of a larger angle, it results in a smaller answer. That's a fact. Cos of a larger acute angle, actually. Cos of a larger acute angle.
Larger the acute angle, smaller the answer.
The larger the acute angle, the smaller the answer. Yes. So larger acute angle, that actually means the cos of the horizontal component of UA has a small answer. The cos of that angle has a small answer. So UA itself must have a large answer to have the same velocity as, to have a large enough velocity to cover the same distance as UB. So since the angle theta of A is larger than 45 degrees, clear? So the horizontal component of A will have a smaller value. Actually, theta of A is 45 degrees, so the cos of that theta is going to be less than the cos of 45, less than 0.707, right?
Yeah.
And if this is going to be less than 0.707, then yeah, that's it. Theta is explain why for the paths of the two projectiles, UA must be greater than UB. Must be greater because this cos theta is less than, angle is larger than 45 and cos of theta is less than this. So to cover the same distance, which is equal to V multiplied by T, the horizontal component multiplied by time, in order to have the same velocity, actually, same distance when the time is the same. In order to have this equal answers, the VA must be large, must be larger than actually VB. Okay, let's verify from the marking scheme as well. Theta must be greater than 45 for the path shown, because cos of theta is less than this thing. Theta must be greater than 45. Theta of A must be greater than 45. But theta of A is greater than 45. Yeah. The cos of theta is less than 0.707, or the maximum range of projectile is at 45. To have a greater range at a greater launch angle, then the initial velocity must also be greater. Range means the horizontal distance that it has covered. And this point that they have given us, horizontal distance covered, this range that they have given us, this is also a fact that at 45 degrees, the distance which is covered is maximum in the horizontal direction. So to have the maximum distance covered, the velocity itself would have a larger value. To have a greater range at a greater angle, the velocity must have a larger value. I think that's a much better answer, that range is max at 45. So to have max range at a greater angle, the velocity must be larger,
Okay.
must be increased. And the axis below sketch a labeled graphs for the vertical components of velocity that can stand for the motion of A and B between O and P. You may ignore the effects of air resistance. Okay, let's look at the vertical motion, vertical components of velocities. Okay, the vertical component of velocity initially. Vertical component can be calculated for UA, it's going to be UA sine of theta, and for UB, it's going to be UB sine of 45. For 45, for sine, it's not the same as cos. For sine, the larger the angle, the larger the answer. Okay, the larger the acute angle, the larger the answer. The larger the acute angle, the larger the answer in case of sines, okay? So now,
Okay.
in case of sine, the vertical component of A is gonna be greater than the vertical component of B because the
Sir, would
theta,
we ever need to explain why it is like that?
why
Like,
this?
could they ask us why the sine, the value for sine theta is larger?
Well, that's because of its graph. Do you know the graph of sine? On the x-axis, you have angles. On the y-axis, you have numbers. This is 90 degrees. For acute angles, before 90 degrees, if you look at the values, as you plug in the angles, the graph starts increasing and increasing and increasing. Or you could just use your calculator, plug in sine of 30, and then plug in sine of 45 and compare the answers. Sine of 30 is 0.5, and sine of
Yeah,
45, 7.
0.707.
Yeah, so it's large. See, for acute angles.
Right.
So now over here, the initial vertical velocity of A is larger than B. So over here on the graphs, the vertical velocity initially is going to be larger for A as compared to B. So A is going to be somewhere over here. B is going to be somewhere over here, lesser. Then what happens? Then as these balls rise up, if you look at the motion of B, as it rises up and reaches its maximum value, what happens to the vertical component at the maximum point? The vertical component reaches its zero, right? Because in the vertical direction, you have acceleration, meaning deceleration due to gravity. So at the maximum point, the vertical component becomes zero, and you only have horizontal component of velocity left. UB cos of 45 is the only component that is left at the maximum height. As in case of A, it has not yet reached the maximum height, so it will still have some value. Okay, it will still have some value. The vertical component will still have some value. And then as it reaches over here, the vertical component will reach down to near zero because that's the peak point, almost the peak point. So now if you draw out the graphs, both of them will fall. Okay, none of them would rise, both of them would fall. In case of UB, it will fall and it would reach zero. And then after it reaches zero, it will rise again. And instead of going into the positive side, it will go into the negative side. Why will it go into the negative side? Because it's velocity, right? It's velocity, it's changing directions. See, it's changing direction. It's coming down. The vertical component has now changed its direction. So the vertical component is now increasing in the negative direction. So this velocity will go on to the negative side of the graph. It will go below the graph. And at time t, it will reach its distance, its maximum value. Basically, by rule, I should make both these areas the same. So let me erase this out. These two areas must be the same because uh, This object has covered the same distance in the two directions. So it's going to be somewhat like this. Okay, the upward distance and the low downward distance are the same. That's why this area and the other area must be the same as well. Okay, this side and this side must have the same area. So this is for B. This is the motion of B. Then after B comes A. For A, it is gonna fall. It is the vertical component of velocity will decrease in its value, but the time at which this vertical component of B had reached its zero value, it would have some value. And then after the time finishes off, the vertical component of velocity will reach zero, meaning after time of t seconds, vertical component of velocity will reach somewhere near zero. So this graph start out from a larger value, go down, somewhere reach t right here. It will reach zero at somewhere around t. It will not go into the negative direction because it has not changed its direction. And the gradient of these two graphs is going to be the same. These two lines are going to be parallel lines. Parallel lines because the acceleration or the deceleration that both of them are experiencing is the same. It's 9.81. In case of velocity time graph, acceleration is 9.81. Clear? Okay, so raindrops are of different sizes and they're asking why would a larger size droplet reach the ground more quickly? Okay, so reason for that is larger droplets are heavier. Heavier means that they would have some net force applying on them. They would have a larger terminal velocity. Larger terminal velocity. And if they have larger terminal velocity, then that actually means they'll reach terminal velocity is what determines the time during which it would reach the ground. Okay, so heavier, larger droplets are heavier. If they're heavier, they would have a resultant force downwards. Resultant force downwards. It would take more time to balance the weight, more time taken to balance the weight by the air resistance, more time taken to balance weight by air resistance. So they reach a larger terminal velocity, larger terminal velocity. And if they reach a larger terminal velocity, and of course if the velocity is larger, they reach the ground quickly. Okay, let's compare it to the Markov scheme. At terminal velocity, resultant force is zero. Yes, we've implied that part. So terminal velocity is proportional to the radius squared. Larger droplets have greater terminal velocity, reach the ground first. We did mention that point, but what about the other points? Okay, for the last point, if at terminal velocity the resultant force is zero, we have implied that as well. Larger droplets require greater air resistance before reaching terminal velocity. We've implied that as well by saying that it takes more time for the air resistance to balance out the weight actually means that they require more air resistance. Larger droplets require greater air resistance to equal or greater the weight. Then these are the 3 points we got. And then drag increases with velocity or air resistance increases with velocity. Larger terminal droplets have a greater terminal velocity, so we'll reach the ground first. Okay, they've mentioned it twice. Can't take the mark twice. We got 3 marks for the answer that we wrote, a terminal velocity resultant force is 0. The terminal velocity resultant force is 0. We implied this: larger droplets, terminal velocity, greater air resistance. We should have mentioned this point as well, that the drag force or the air resistance increases with velocity. Air resistance at this point has to come first, has to come over here. Air resistance increases with velocity. Okay, you get the idea behind this question. What would be the net force acting on the object? Initially, it's gonna be
The weight.
the weight itself. The weight will cause acceleration equal to 9.81 initially when the resistance is 0. As time passes, the speed will start rising as a result of this acceleration. Is that true? The speed will start
Yeah.
increasing, right? Now, as the speed increases, the air resistance also increases.
Right.
Also increases. Now, if the air resistance, which is the upward force, increases, let me call it R, this air resistance, the increase in air resistance starts balancing out the weight, and then the net force acting downwards starts approaching 0. And then a time comes when it becomes 0 and the resistive forces become equal to the weight. At that particular time, this ball would have gained a certain velocity, which is called a terminal velocity, which was a velocity that the ball, which was a result of the velocity that the ball, which was a result of the increase in the velocity due to the acceleration of this ball, right? Now consider a second ball that has a smaller weight. Let's say its weight is W upon 2. As initially its acceleration is also going to be 9.81. If its acceleration is 9.81, it will start gaining some speed, right? If you start
Yeah.
gaining some speed, then the air resistance will start rising again because it rises with speed. Now its speed will keep on rising as long as there is some difference in the air resistance and the weight, as long as a net force downwards is present. But as this net force becomes 0, the speed becomes constant at that particular value where it has reached. For example, initially the value of speed was 0, then it increases to 10, then increases to 20, then it keeps on going until a time comes when the resistive force balances out the way, the net force becomes 0. That was a time when the velocity might have reached 50. Then it will not increase further, but rather will stay at this velocity, and it will keep on falling at this particular terminal velocity. Whereas if you compare this example with the ball on the left, which is the heavier ball, it will take more time for the resistance or for the air resistance to balance the weight. Taking more time means that net force is present for a longer period of time. If the net force is present for a longer period of time, then that means the velocity which was increasing, it increased to a larger value. It was 0, let's say it was 10, it was 20, it kept on increasing. But since the time it took for the air resistance to balance the weight was larger, since it required more air resistance to balance the weight, more air resistance is required to balance a greater weight, more air resistance needed to balance the greater weight. Therefore, a larger velocity had been reached, and for instance, it reached a value of 70 meters per second when the air resistance finally was able to balance out this increased weight. So now this ball will fall at this velocity, and now this velocity is going to be the terminal velocity of this ball, the heavier ball. If you compare the terminal velocity of the heavier ball with the terminal velocity of the lighter ball, now they are different because of the difference in their weight. Now do you get it? What do I
Yeah.
mean by different terminal velocities? Okay, let's assume 1 centimeter represents 1 meters per second, and that actually means 8.5 centimeters would show this vector, 12 centimeters would show this vector, and you'll draw it and you'll get your answer. Okay, so 12, let's start off from here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. This is your first vector of 12 meters per second. Of course, you're going to use a ruler, and then you come down 8.5 centimeters. 1, 2, 3, 4, 5, 6, 7, 8, and 8.5 somewhere over here. This is 8.5 meters per second. And then what are they asking us what to do next? Just need to label it. Also, we've labeled it as well. Hence determine the resultant velocity of the vector of the rain. To determine the resultant velocity, instead of drawing it here, I'll draw it on the head of it. Then draw a horizontal line like this, and then measure its length. Well, we can measure it using the ruler and then get the answer, and then that's the answer over here which you need to write. Then the direction of the rain is going to be, of course, it's horizontal, it's diagonally. If this is north and this is east and this is south, it's southeast or east south, southeast actually. Southeast is the direction, and just writing southeast won't be sufficient. You also have to measure this angle. Okay, measure this angle and then write it as this degree from the east. Let's compare it with the answers they have given us. 1 centimeters to 1 meters per second use, resultant correctly identified, such stuff. And see, they have asked us for the degree as well. And then these are examples of calculations that they have given us.